Hello, folks. Okay, I want to work through a bit of an example to get us back into the habit of thinking of different data structures and their representations, using structs for them, and to get some practice in with dynamic allocation and deallocation of arrays. So what we're going to do is we're going to keep track of a queue of strings. So essentially, we can add new strings to the back of the queue, and we can pull strings off the front of the queue at any point in time. So just a way of keeping kind of an ordered series of strings that we're going to play with. So we'll have something to add a new string at the back, something to remove the front string from the front, and we'll see what we can do here. Now, what I'm going to use in terms of an implementation is what's called a circular buffer. So the idea is it's just an array, but since we're going to be adding things at the back and removing things from the front, what we'll have to do is keep track of where in the array the front element is right now, the front string, and where in the array the back element, the back string is. And if you think about it, if we do a whole bunch of inserts, let's say we insert stuff and we fill up the whole array. So all of the positions are full. And we do a bunch of removes at that point. And so we're taking away things from the front. Now we've got a bunch of positions, say position 0, 1, and 2 in the array are empty. And the rest of them are full with the front in position 3 and the back at the whatever the last spot in the array is. Well, I've got empty spots in the array, so I should be able to do more inserts. I should be able to add new elements to the back of the queue. Now, of course, they can't go at the end of the array because that would run it off the end, right? We have the last position, the back position in the last spot in the array, but those ones at the front are empty. And so we'll have this idea that the array wraps around, or that our queue wraps around. And so the front might be in position 3, but the back might suddenly be in position 0. And so you've got this notion that you've got some spot in the array where it begins, and then you go kind of up the array till you hit the end, and then it wraps around and you start at the front and keep going from position, or starting at position 0 again, and going up through the array spots until you reach whatever the last element currently is in our queue. So we're going to have this idea of kind of a wraparound circular buffer, circular array, where, in fact, it's of course just a normal array, but we're using it as if the positions wrap around, where once you go off the end, you start again at the front. So this is the idea we're going to aim for, and we're also going to aim to make it resizable, so that if we ever get to the point where I've got an array of size n, and I've got n things actually stored in it right now, and I want to insert one more, then I'll say, well, the array is not big enough, so what I'll do is create a bigger array, move all of the data across to that, and delete the old one. And so we'll have this idea of being able to resize it, being able to grow the array when we need to. So these are the objectives we're aiming for. An array implementation of a queue, we can insert one item at the back at a time, we can remove one item from the front at a time, and we always go in this cycle of, we can add as many things as we want, we can remove as many things as we want, of course, as long as it's not empty. And we'll just keep going. If we wind up in a scenario where we're putting the next element in the last position of the array and there's space available at the front of the array, the next insert is going to wrap around to the front. And again, we're going to use dynamic allocation, pick some size for the beginning, and anytime the array fills up and we need more space, we'll dynamically allocate a new, bigger version and move stuff across, get rid of the old one that's too small. So there's the idea. And again, just in terms of an example, say we have an array of size 5, so we've got array position 0, 1, 2, 3, and 4 that are available. And we go through and the user does a bunch of inserts. So we put 10 in position 0, and then 17, and then 30, and then 29. So position 4 is still free, but the others are all taken. The user does a couple of removes. So it takes out the 10, takes out the 17. And so now we've got stuff in just positions 2 and 3, and the others are empty, right? So whatever's in 2 is in the front. Whatever's in 3 is in the back of our queue, if you like. We do a we insert another one, so that's going to go in position 4. So we've got 2, 3, and 4 filled now. And then we do another insert, and this is where the wraparound comes in. We've got the first thing in position 2, second in position 3, third thing in position 4, and then the last thing is in position 0, and the array wraps around, or the buffer wraps around. So there's the idea. In terms of keeping track of what's going on, again, we'll need something that keeps track of which position in the array has the front element right now, and which position in the array has the last element, the back element right now. And what I'm going to do is the first insert that I do is going to put, I insert a value. I'll start off by default putting it in position 0 in the array. And for that moment, that one and only element that's in there is both the front element and the first thing in the list and the back thing in the list, the last thing in the list. So these front and back values are both going to say, well, position 0. Position 0 is the position of the first thing, and it's the position of the last thing, since there is only one thing. So what I'm going to do is when there's nothing in the array, I'm going to set front and back to -1, just so it's absolutely clear to me that right now there's nothing in there, I'm not using it. So this is what I'm going to do. Front will have the value of the position of the front element, back will have the position of the last element, and we'll set them both to -1 anytime we have nothing stored. So there's the idea. Anytime we do a new insert, we're going to be incrementing the back. Anytime we do a remove, we're going to be incrementing the front, right? Moving it from the first position in the array towards the last position in the array. And as long as there's still space available, when we hit that last position, we'll wrap around and start over at position 0. So there's the idea. When we're trying to figure out how many things we've currently got stored in this queue, in this buffer, if front and back are both -1, that means we've got nothing. So I can just return a size of 0. But otherwise, I can say, well, if I take the back position minus the front position, that almost gives me the number of things stored, but it's kind of off by 1. So you take 1 plus the back minus the front, and that would give me the right size, unless there's wraparound. Because if there's wraparound, then the back position is actually less than the front position. So what we can do is, if back is less than front, then essentially we just add the size of the array in to correct where things should be. So we can go through and work out the size simply from front and back, and however big the actual array is. So we don't need a separate variable to keep track of the size. We can just work it out from front and back. So again, if we're in a normal situation, if you like, where front is a lower value than back, then we can just do back plus 1 minus front. That'll give us the right size, and otherwise we add n. And again, it's empty if both of them are -1. So we'll work through some code examples of this in just a second. Now, one of the things that's kind of handy is if you ever want to cycle your way through the elements that are currently in the buffer, if I want the kind of ith thing in my list of elements, right, not the ith position of the array, but the ith thing in my n-queued list, if you like, I can take the front position, so wherever the element actually is in the array, add the position in my queue, so if it's the 0th thing that I haven't queued, or the first thing I haven't queued, or the 27th thing I haven't queued, add that to front, and then I just have to account for the fact that this might wrap around, so I take it modulo the size of my array. And so if we get wraparound, that'll take it around to position 0 or 1 or 2 or 3 or wherever it winds up. So take our front, well, it should be our front plus our I. I really should have brackets around that. Front plus I modulo n. So there's the idea. I should actually make a little note here so I correct that on the slide. And again, this gives us the position of the currently enqueued item. So the other thing that we wanted to mention was this idea of resizing the buffer when we need to. If it ever completely fills, if the number of things that we've got enqueued right now ever matches our array size, then to do any subsequent inserts, we're going to need a bigger array. So again, what we'll do is allocate a new one that's twice as big as the current one, check to make sure that the allocation actually succeeded, copy all of the current content across to the new one, make sure that whatever pointer we're using to keep track of where the array is updated to this new one, and delete the old one. So that's the objective, right? That's the kind of logical view of where we're going with this. And I just want to have a bit of a play with some code to actually do it. So let's see how we can go here. So what I've got here is my circbuff here, and my circbuff.cpp and circbuff.h are the ones that are going to implement this kind of circular buffer, this queue. And then data store is just a program to try loading it and using it and seeing if it actually works. So as far as our circbuff goes, let's have a look at how we'll structure this a little bit. So what I'm going to go with is this idea of we'll use a struct to hold all of the information for our circular buffer. And again, it'll have integer variables to keep track of the front and the back, the position of the current first thing and last thing that we've got enqueued. We're going to come up with, again, a queue of strings, if you like. So what I'm going to do is use a dynamically allocated array of strings. So I'm just calling it buff here. So this is going to be a pointer. So we've got basically a string pointer here. And once we go off and ask for an array of strings, this is where we'll keep the address of it. I am going to throw in a variable to keep track of the size, but again, we can compute the current size just from front and back if we want to. All right. Oh, no, pardon me. I misspeak. So size is going to be how much space I actually allocated in the array. So this is the size of the array, whereas the number of items that we currently have enqueued will compute from front and back. Sorry about that. All right, so we'll have a function to go through and allocate the array in the first place. So when somebody says, I want a circular buffer of size 20, this is the function that's going to do it. So they pass us the circular buffer that they want initialized, right? It's passed by reference to make sure that we can actually change the pointers in it. They tell us how big an array they want, how big a buffer they want, and we'll go through, we'll try and allocate that array of strings. We'll initialize front and back to -1. We'll initialize the size to whatever the size was that they requested, and we'll return true or false depending on whether it succeeded or failed. Now, if it failed, maybe we'll be a little bit more careful and we'll make sure that the size in here reflects the fact that we didn't actually successfully allocate anything. So maybe we'll set the size, the allocated size to 0, as well as the buffer pointer to null if this thing fails. But we'll manage to return to them, yes or no, did I succeed in initializing this the way you wanted? Now, since we're doing dynamic allocation, we need to do dynamic deallocation once we're done. So we'll have another function where we pass it the circular buffer, and it will go through and deallocate that array of strings. So that'll be the one that we call kind of at the end of the program if allocation succeeded in the first place. Maybe you'll have a function to go through and say, okay, well, how many things do I have stored right now? So again, that's doing the back +1 minus front, and adding n if necessary to correct for wraparound. So that's the one that's figuring out how many elements we've got stored. We'll have a function to go through and replace the old array with one that's twice as big if necessary. And again, this one's going to return true or false depending on whether it succeeds or fails. Because again, if anytime we're doing a dynamic allocation, it's possible that it fails because there's just not enough memory. So This one will go through, try and create an array that's twice as big, move everything across, adjust the pointer, delete the old one, return true or false whether it succeeded or failed. All right, one to go through and try inserting a new element at the back, updating back, wrapping it around if it needs to, again returning true if it works, false if it doesn't, because this might need to call resize if the array is actually full. And maybe the other side, a remove, so we'll go through and try and remove the front element. Again, updating front to point to the next position, wrapping around if it needs to, and returning true or false. Pretty much the only way this one can fail is if they try and do a remove when we had nothing stored. So if front and back were -1, then this effectively the size was 0. Or I guess if the array had nothing in it. And then one more for debugging purposes than anything else, where we can print the current contents of the buffer from the whatever's front in the queue to whatever's last in the queue. And so that's the idea. And if we have a boo at, I'm not going to go into all of these beasts in detail, but again, when we're going through, we can say, okay, well, when I'm initializing it, they give me the buffer that they want initialized. They tell me how big they want it. I'm going to initialize everything as if it's going to fail. So I'm going to set my front and back to -1s to indicate it's empty, my size to 0, my pointer to null. And so that's the kind of default nothing in its state. And then we'll try the allocation and update things if it works. So if they gave me a valid size, if they asked for a negative size, or if they asked for size 0, then I can't do anything about it. But as long as they give me a valid size, I'll try and allocate that new array of strings of that size, right? And again, that will return either null if it failed or a pointer if it worked. And so I store that as my buffer. If it worked, then I can go on and use this happily ever after. But if it didn't work, so if that buffer return was null afterwards, then I'll give them an error message, didn't work, return false. Otherwise, I'll update the size and say, yeah, I actually created, something of size 10 or 20 or whatever it was you asked for, and I can return true. So we can go through and take a reasonable stab at that initial allocation of the array. And then the flip side was where we want to go through and deallocate it at the end. And we really just want to make sure that before we try and deallocate it, we want to make sure that there was actually something there to deallocate. So if that buffer pointer was already null, if the buffer pointer is not null and we actually have something allocated, we have a positive size, then we'll go through and do the delete. Right? So we're just making sure that we don't try and delete something that hasn't been successfully allocated. All right, the resize one was one of the interesting beasts where we want to take that existing buffer, create a new one that's twice as big, move everything across, and get rid of the old one. So again, first thing we're going to do is make sure that there's actually a buffer there to resize. So if they gave us a circular buffer with a null pointer in it, there's not really much we can do, right? There's nothing there to copy across, or the size is 0 or less. Then again, we'll give them an error message. This can't work. You didn't give me a validly initialized buffer to work with in the first place. Otherwise, we'll create a new size that's twice as big as the existing one, try and allocate it, and again, test if it worked or not. If it didn't work, then we'll just bail out and we won't change the buffer that they gave us. If we get past that, it's because it did work. So we'll find out how many elements were in the buffer in the first place, how many things we've got to copy across. And I'm going to copy them into the front of this new bigger array just to kind of clean things up if we had wraparound in the old one. So we'll figure out where the elements are in the old one. So working from the front to the back, so for each of those different positions, I'll take the front plus whatever position it is in the queue, modulo whatever the size of the old array was, and that gives me the position that I'm going to stick it in my new bigger array. So I'll just copy it across from the old position in the old array to the new position in the new array, and set my front and back, and we should be good. Right? All we have to do is get rid of that old allocated one, right? Deallocate the old one, and make sure that we update our buffer to point at the new one, and our size to the new size, and we can return true. We're done. Right? So you can go through this idea of resizing whenever you need to. Right? And this won't get triggered until somebody tries to do an insert when the array is already full. All right, the get current size is pretty much just that idea that I talked about. If they're negative ones, then it's just 0. Otherwise, we take 1 plus the back position minus the front position. Check to see if there was wraparound there. So if back is less than front, then we need to add the size of the array. Otherwise, we should be good. All right, inserts, again, pretty much the idea that we were talking about. Check to make sure that the buffer actually exists, right? So we've always got this error checking to make sure that we're not trying to access an invalidly allocated array. We'll tweak things a little bit based on whether the array was empty or full or somewhere in between. So we'll figure out how many elements there are in there. If there was nothing in there, then this is the, we're inserting into an empty queue. So we'll just put it in position 0, front and back will both refer to that. So right, we'll put the element in position 0, update front, update back, and return true. Otherwise, we'll see if we need to resize. So if it's full, then we'll resize first, and if that doesn't work, we'll bail out. So that takes care of resizing if we need to, and once we know we've got enough space, then we're inserting at the back. So we're moving, so back refers to the position of the thing that's currently last in the queue. So we're moving to the next position, seeing if we need to wrap around. So if this takes us kind of up to off the end of the array, then we'll wrap around to the front position. We know that that's free because we've already checked that we have enough space. Stick the current string in that new position, and we're done. And then remove is going to be just a similar idea, but working from the front. Right? We'll go through, find out how many things are in there right now. If there's nothing in there, then we'll give them an error message. I can't remove from an empty buffer. Otherwise, we'll grab the front string, and this might be the only string, in which case we want to set front and back to -1s to make sure that we indicate it's empty. Otherwise, there's more stuff in there, so we just have to increment front. This might involve it wrapping around, so we'll check and wrap it around to the front position if we need to, or to the 0 position if we need to. And again, we're done. So we can go through and build up our logic sort of piece by piece for the most part. Right? Printing is the same idea as we discussed earlier, where first we'll make sure there's actually something there to print. If there is, we'll find out how many things there are. And then for each position in the kind of logical queue, if you like, we'll find out where that is in the array. So if we take the front position, where the front element is located in the array, add which position in our kind of logical virtual queue we're interested in, take that modulo the size of the array. That tells us what actual array position that element's going to be in, and we'll just print that out. So again, relatively straightforward if we think of the individual steps, the individual functions kind of piece by piece. There's just, again, a lot of housekeeping we have to make sure that we take care of. All right, and again, just a quick example of playing with some of that. Most of this is just going to be logic for going through and playing with things, but we'll go through and ask the user for what size of an array they want. We'll try to allocate it, right? So buffer is going to be my circular buffer here. I'll try and allocate it with whatever size they asked for. And then I'm going to repeatedly ask them for commands. Do you want to insert, remove, or print? I'll apply their command to the buffer and just keep going until they decide to quit. So we'll just keep going through this cycle. And again, get size is just your typical get an integer and keep going until they give you one. The process is saying, okay, well, here's the buffer, here's the command, insert, print, remove, quit, whatever it happened to be, or help. And we'll just call one of those buffer functions that we just described. I want to insert into this buffer some word. So ask the user what word, grab it, insert it. Right? That kind of an idea. So you can have a boo through some of this if you're curious. But again, the ideas themselves aren't too horribly complex. Let me just, again, recap where some of this stuff is. If you go back to our page of lecture resources, well, the video is the one that we are currently talking through. The slides are the ones that I just ran through. And if you follow that other link, it'll give you, you can have a look at the makefile that's in use, the code for the data store, the code for the circular buffer. So it is all available there if you want to have a play with it. So I will leave that to you.